Oh, hold on just 1 second.
Hey everyone, for your information, we're still waiting for our guest lecturer for today, Vivek Srikumar, to join us. It might be a minute.
Hey, shall I
Hi,
try
Vivek.
sharing screen?
Welcome. Yes, you can.
All right. Tell me if you see something reasonable. Okay, cool.
That looks great.
The only catch is I cannot see the chat. Oh, actually I can.
Yeah, if you want to, I can also monitor the chat for you and interrupt you if there's a question.
That's also fine. Yeah.
Okay, let's get started. Thanks everybody for showing up. Today we have a guest lecture very kindly given by Vivek Srikumar. Vivek is an associate professor in the School of Computing, and his research area is natural language processing. And so Anna and I figured we'll just invite the expert to give us an overview of what NLP is like, and then we will follow up with a practical NLP lecture in the near future. So Vivek, please take it away.
Awesome. Thanks for inviting me. This is a fun lecture because it's just me telling you about how cool language is, something you probably already know. And I'll show you a bunch of examples of things that we do in NLP. And if time permits at the end, I'm going to show you some demos of state-of-the-art NLP systems that you can also play with after class. All right, so what is NLP? In some sense, it's a rather ambitious goal, just like trying to do a screen share, apparently. So I'll try that again. So it involves, NLP involves this agenda of replicating in computers a phenomenon that, to our best knowledge, only humans exhibit in the entire galaxy or the known universe. So we have never seen language in any other species, anywhere else, and we are hoping to somehow replicate this uniquely human trait in programs. So the idea here is we want to make computers understand natural language. Turns out it's not that easy. And people have been trying this for the last 50 plus years. And something remarkable happened in the last 20 years, which was the use of statistics and data science. And that's where we are in the present state of NLP. And then towards the end, I'm going to talk about this, what does text understanding mean and what we can do with these things. So to start off, I'm going to ask you a question, and feel free to unmute yourself and answer the question, or you can use the chat if you want. Let's say I give you a story and ask you to read the story and answer a question. So here's a story about Sarah Abel and Martin the monkey. And what I would like you to do is tell me, what town does Sarah Abel live in? Any one of you.
I mean, humans, it's obviously Bananaville.
Yes, it is obviously Bananaville, but here's the hard question. So yes, you are right. It is Bananaville. The hard question is, why is it Bananaville? How do you know? Can you prove it to me?
The logic would be that she lives in the same town as Martin, and Martin lives in Bananaville.
That's excellent. Let me make it even more complicated. Let me take what you just said and make it ridiculously complicated, laughably so. So we don't know that Sarah Abel is she. In fact, I don't know how you agree, but probably we all agree that this is a person, Sarah Abel, and we agree that it's also something, this string called SARAH space ABLE is also the same thing as this other string called SHE. This is a task in NLP called co-reference resolution. How do we know which pronoun, which entity a pronoun refers to? After doing that, we do, okay, this is, the math is going to fail because I switched PowerPoint versions, and of course that ruins things. This is just supposed to say, for every town, for every X that's a town, the town that she lives in is the same as the town that Martin lives in. That's what this sentence tells us. I'm going to elide over the ridiculous formatting, but this idea of taking a sentence and converting it into some sort of a logical form is called semantic parsing. After that, we somehow have to agree that Martin is same as Martin the monkey. It's not some other Martin. And again, it's co-reference resolution. We have two strings and we want to know, do these things refer to the same real world entity? Once we do that, it's easy. We look at the grammar of that sentence. Martin the monkey lives in an oak tree. The oak tree is located in Bananaville. And all of this information, these two things are called are from a task in NLP called semantic role labeling. And once we do all of these things, we have to somehow solve a logic puzzle. We have to know that if Martin the monkey lives in an oak tree and the oak tree is located in Bananaville, Martin the monkey lives in Bananaville. And if Martin the monkey lives in Bananaville, then Martin lives in Bananaville. We're just talking about strings here. Remember, we are these are, because we live in the world, we know that Martin and Sarah are names, and Bananaville and oak tree and such things. We know about these things. But then we also know that she lives in Bananaville. But there's a problem here, which may not be obvious. All we know is from here, she lives in the same town as Bananaville, provided that X is a town. How do we know that Bananaville is a town? We probably have never been to this town called Bananaville, but somehow most of us would agree that Bananaville is the location. And then after that, it's easy. Once you know that she lives in Bananaville, you know that Sarah Abel lives in Bananaville. Now, other than the somewhat awkward math formatting that's going on here, there is I want to mention two things here. Most of us would agree that the answer is Bananaville, and almost none of us would have actually gone through this really complicated process explicitly in our minds in order to prove that the answer is Bananaville. We can read the text and perform this kind of processing, solving all these different named tasks like semantic parsing and coreference resolution and all these things in an instant. That's what we want machines to do. We want them to read stories, understand them, act on them. We want them to listen to what we say and play the song that we want and make our slides correct and all these things. So this is really a hard problem. And yet, we seem to do it so easily. We seem to generate language effortlessly. We seem to understand language effortlessly. If you think about science fiction shows and movies, computers struggle with simple things, but somehow they always seem to be able to talk and understand language well. It's something that's so natural to us that we take it as a given. That's really what we want computers to do. We almost generate and understand language effortlessly, except language is actually not easy. Language can be ambiguous. Here's a headline from some newspaper in 2013, Tuna Recall blamed on seal. And I'm not kidding. When I first saw this headline, I was confused. I did not know which seal was getting the blame. Was it the animal, the seal? Was it the musician? Was it some sort of a contract? Was it some military seal? Was it the thing that is using the thing that's used to seal the can? And I still don't remember what the answer is because I got so caught up with the ambiguity and exploring it that I never bothered to read the rest of the article. But we routinely use this kind of ambiguous language. When I say olive oil, I mean it's olive oil made from olives, and baby oil is oil for babies, not from babies. An easy mistake to make, but an important one. A diamond ring is a ring with a diamond. A gold ring is a ring made of gold. A nose ring does not have a nose in it. In fact, it goes around the nose. And we use the same sort of lexical constructions. And this ambiguity is something that we navigate so easily. I mean, it's actually kind of fun to see people understand this kind of ambiguity because it makes you respect what we can do. But ambiguity is not just about how words are ordered here. These kinds of phrases, entire sentences can be ambiguous. If I say I ate sushi with tuna, it means that you ate both sushi and tuna. If I say that I ate sushi with chopsticks, it means that I ate sushi using chopsticks. I definitely did not eat the chopsticks. And when I say I ate sushi with a friend, I did not eat the friend or use the friend to eat sushi. I accompanied the friend in eating sushi. The same word, almost the same construction, means very different things. And again, it's another example of ambiguity. But if I say I saw a man with a telescope, then did I use the telescope to see the man? Did I see a man carrying a telescope? I don't know which of these meanings it is. You need further context. And I'm sure you've seen a lot of jokes that essentially use the same idea, the idea of exploiting ambiguity, where you are forced to read it in one way and then the punchline tells you to read it the other way, or something like a stolen painting found by a tree. The thing is, language is also structurally complex. If I say I'm allergic to tomatoes and also fish, doesn't mean that fish are allergic to tomatoes. And this kind of structure is something that we almost easily understand most of the time. I'll give you a more kind of a complicated example of these structural complexities using Dutch. Here's a sentence in English first. Jan saw the children swim. In Dutch, well, before we go to Dutch, you can think of this natural language processing task of parsing, which is identifying the syntactic structure of sentences. Some of you may have been unfortunate enough to be forced to diagram sentences in high school or something like that, and that's what this is. You are asked to identify what is the subject of the verb here, of seeing. Who's doing the seeing? It's Jan. And who's doing this? What is Jan seeing? It's the swimming. Well, who's doing the swimming? It's the children. In English, these kinds of diagrams are easy in the sense that they don't cross each other and you don't have to, there's this hierarchical structure. Let's go to Dutch. In Dutch, the same sentence is Jan, der kinderen zag zwemmen. Jan, the children saw swim. I'm just translating word by word. It's the same sentence. Jan saw the children swim. But in English, you had the verb and the doer of the verb are right next to each other. The children are doing the swimming, Jan's doing the seeing. In Dutch, you have to essentially push these words into a list and then start going back through this list again. Who's doing the seeing? It's Jan, the first noun. Who's doing the swimming? It's the children. You might say, yeah, this is easy. I can remember two things. Okay, let's add another character. Let's add Pete. This sentence means Jan saw Pete help the children swim. In Dutch, it's Jan, Pete, the children saw, help swim. You just have to remember the order in which the nouns show up. And then when the verbs show up, you have to just kind of start matching. Okay, three things might be easy. Let's introduce Marie. Jan, Marie, the children saw, help teach swim. At this point, most of us, even Dutch speakers, might get a little annoyed because in English, it is Marie is teaching. The sentence is Jan saw Pete help Marie teach the children swim. In Dutch, it's Jan, Pete, Marie, the children saw, help teach swim. The sentences mean the same thing. And I'm not saying that Dutch is necessarily a harder or easier language. It's just another language which is as complex as any other language. And it just has this interesting complexity. So we can't get rid of Dutch. No, that proposal won't be met by taken too kindly. So, when we say natural language processing, we're not just talking about English, we're talking about every single language, English, Dutch, Swahili, languages that are extinct, languages that are evolving as we speak. And all of these, we are hoping that computers will understand them. We will deal with them. Those of you who've seen an introduction to models of computation, natural language is not context-free. If that means nothing to you, it's not going to affect the rest of the talk. But these are just some linguistic phenomena. There are so many linguistic phenomena. Think about metaphors. When I say something makes my blood boil, I'm not talking about literally my blood heating up and starting to bubble. I'm just saying that I'm angry. Or when I say the White House said, I'm not talking about a talking building. And we implicitly understand these things. And these kinds of linguistic phenomena are used by poets. Well, not just poets. We use this. We construct these kinds of sentences all the time in our daily language. When we talk about the glass ceiling, it's a metaphor or something else. Or when in Shakespeare, we hear about Juliet being the sun, it is the east and Juliet's the sun. It does not mean that Juliet is a hot ball of burning fire. And we are very creative with these kinds of idioms. I mean, the idea that Juliet is the sun was first said by Shakespeare. At that point, nobody else had ever used that exact sentence, and the audience immediately understood it. Isn't that cool? I mean, there was an idea in Shakespeare's head. He wrote it down using this really complicated metaphor. His actor said it, and then the audience understood the idea that was in Shakespeare's head by using this sort of a complicated coding process. And the problem is we make up things all the time. We make up words, we make up constructions. Language is not something that is just in a dictionary, it's alive. These are just a couple of examples of sentences or poems or phrases that contain words that are not in the dictionary. The bottom one is from Lewis Carroll. Some of you may have seen this. And if you remove all the words that are not in a dictionary, you're left with pretty much nothing. And yet people kind of read this poem, and I don't know if they understand it, but I don't. But at least it's not considered garbage. So it seems like the situation is hopeless. If people make up things on the fly, and there's a whole list, a laundry list of complicated linguistic phenomena out there, and we just use this really complex structures all the time, how could there be any hope for people understanding language, let alone computers? But I'm going to argue for the rest of this talk, and then I'll show you examples that this is not a hopeless situation. We already are in a place where it's far from hopeless. There are all these virtual assistants that supposedly understand language sometimes, and they do a reasonable job of doing what we want. How could it possibly understand these kinds of complicated things? Next time you want to talk to one of these assistants, try asking it about a metaphor or an idiom. It may not succeed. Sometimes it might, sometimes it won't. Web search is a cool example of how language is just used in a way to interact with computers. You can ask Google what color are bananas, and it will tell you that they are mostly yellow, even though it shows you an image of mostly not so yellow bananas. You can ask what's the capital of Utah. It will tell you correctly Salt Lake City. You can go to Google Translate and give it that Dutch sentence, and it will correctly reorder the words and construct the corresponding English sentence. And you can actually use Google Translate to reasonably read newspaper articles that are written in a language that you can't even read the script of. That is so cool. So how did we get here? So for the next maybe 20 minutes or so, I'm going to take you on a historical tour. First, I'll talk to you about old NLP systems and the underlying ideas, the sort of a underlying philosophy that was behind old NLP systems. And then I'll talk about the problems with them and tell you why or how we can fix it, or how we've been able to fix it. There are some of the early NLP systems had these cool names like Eliza, Parry, and Pundit. And these were essentially rule-based systems. Someone, often the person whose name shows up next to the system name, wrote a program which had a bunch of rules that would read some text and manipulate them using those rules, essentially writing down the rules of grammar. So Eliza and Parry are a curious pair. Eliza was a psychotherapist, and Parry was a paranoid schizophrenic. And there is a cool transcript of Eliza and Parry chatting with each other. You can talk about these information extraction systems, our Shudlu, which is a program that took textual input and could, in some sense, reason about this simulated world called Block's world. And the thing that was really interesting and cool about these systems was that they had really rich representations about text semantics and also about the world, about things like if a block cannot sit on another block if the other block already has something on it. Things that we might take as common sense, but all of this was baked into the rules that were that essentially were written for these systems. So the main lesson here is if you have a rich representation of language and a rich representation of the world, you can do remarkably cool things. You can play with Eliza, and if time permits, maybe I'll show you a demo of Eliza. But it still seems surprising. There's a famous story of one of someone who was a secretary to the professor who was working on this thing, who was using Eliza, and in the end, after the whole system was used, the student or the professor wanted to look at the transcript of the conversation, and the secretary got offended because she said it was a private conversation that should not be that you should not read. which means that, that person was willing to, even though that person knew this was just a bunch of rules, they were willing to acknowledge, they were willing to kind of, almost pretend that this was a person, a therapist, and reveal private stuff. This was really cool, except there was a problem. The problem with a lot of AI of that era, it's called now good old-fashioned AI, it worked really well, except when it didn't. It worked really well in limited cases. For a small set of examples, these were almost like proof of concept, and they took so much effort to create, because there was one person or maybe a team of people who had to essentially implement by hand all the logic that went into a chatbot, for example. And it really didn't generalize well, because there were too many handcrafted rules, and language is not something that is deterministic. And this was a problem. Handcrafted rules, unfortunately, don't reflect how language works in practice. Despite what we are told in grade school about grammar, language is more a probabilistic object. And that takes us to the modern era of NLP. Around, say, the late 80s and early 90s, there were a few research groups around the world were starting to explore this idea of using data, of using statistical methods, or if you want to use a modern terminology, using machine learning. Statistical NLP was starting to kind of become more popular in the late 80s, for example, in IBM's translation project. The intuition was, why do I need to write down a bunch of rules when I can go to a library, take every single book that's ever written there, digitize it, and have a program that extracts statistics of language use from these books. And I can build NLP systems that essentially play back these same statistical decisions. So why would I have to ever write down the rules of language? This was an idea that started becoming popular in AI in the 1990s, but it's actually a really old idea. This is a photo of Firth. Firth had a paper, has this famous quote from his 1957 paper, "You shall know a word by the company it keeps." What this means is, if you really want to understand a word, you need to understand the context in which it is used. A side effect of that is, if you have two different, if you have two different words that seem to appear in the same context all the time, they share aspects of meaning. In other words, you don't really have to have rules of grammar and such things. You just have to look at the co-occurrences of words. This is a pretty old idea. I mean, the quote on the screen is from 1957, but traces of this idea show up in writings of Firth from the 1930s, 1934. He had a paper where it shows up, and in that he talks about older work from German philosophers in the 19th century with similar ideas. So this idea kept coming back again and again. Well, this idea has been mechanized in today's modern artificial intelligence. Let's see some examples. Imagine that you have to build a spell check system that takes a sentence like this: I would like to eat a dash of cake. And you have to decide whether it's P-E-A-C-E or P-I-E-C-E, whether it's peace or peace. And you have two choices. And the idea here is, you train a binary classifier, a decision system that takes the context, all of this stuff around the word, converts it to features, and predicts a probability for, should it be this piece or this piece. This is a way in which modern, or not this exactly, but a grown-up version of this is the way in which modern spell checking systems kind of work. If you've used Grammarly, for example, there's a little bit of this going on in Grammarly. The idea here is you collect a lot of data of text that people write, assume that most of the time people write the right thing, and you just ask, is this more probable in the context, or is the other piece more probable in the context, according to a big corpus of text that exists out there. So you collect some data, you build a statistical model, you train the model, and you make a profit. But what do these words actually mean? At this point, we're not actually looking at the meaning of words at all. We're just looking at treating them as strings. What do they mean? How do we represent words in a way that computers can understand? You can't just use the spelling, because spelling can be rather misleading. Bunny and Sunny are just one letter apart, but mean very different things. Bunny and Rabbit are, I don't think they don't share a single letter, but they mean the same thing for all practical purposes. So we can't use the spelling of words. We can, of course, use the dictionary, but the dictionary is also full of words. So we're just making it another problem. So can we learn the meaning of words from data? This is another sort of an old idea. Once again, from the 1990s, you can represent words by a high dimensional vector. What I mean by that is you represent every word by a list of numbers, and every entry in that list would be how many times, for example, does the word digital show up before or after the word aardvark? Never. How many times does it show up before or after computer? According to this particular set, 2 times. How many times does the word information show up within a few words of the word data? Apparently 6 times. How many times does apricot show up with sugar? Once, but never with computers. We have Apple computers, but not apricot. So this is a big list of words, and this again operationalizes Firth 1957. The meaning of a word, according to this philosophy, is just this list. Well, we get to decide what meaning is. So what we have here is we can decide that the meaning of the word information is this list of numbers. A newer idea is to say that, this list is really large. How big can this list be? It's as big as the dictionary, because there will be one column for every word in the dictionary. Can I apply something like principal component analysis, or a more complicated version of that, to essentially just compress this and maybe find, say, 300 numbers that represents the meaning of each word? These array of numbers or a vector of numbers are called word embeddings. And word embeddings are a driving force behind everything that we consider as modern successes in NLP today. All the demos I show you are built on top of very complicated versions of the same idea that I just described. Words are converted into these vectors in some fixed vector space, and you just use that as features for some classifier. Let's look at another example. Another task in a natural language processing is called part-of-speech tagging. This is one of those tasks where the name essentially gives away the whole thing. The goal of the task is to tag every word in a sentence, like this thing here, with its part of speech. So the koala is a noun, drinking is a verb, green is an adjective, and ink is a noun. So we have this is a prediction task where we are given a sentence and we have to predict one label for every word here. But also the labels kind of influence each other. If I tell you that the word, if I hide the word koala and I show you a determiner, the dash drank the green ink, I can ask what label could show up here, and most of the time determiners are followed by nouns. I don't have to really look at this word here. If I have, you cannot have the drank, you can have a noun or an adjective. So the standard solution here is to train something called a sequence model, where we want to assign a probability to this entire sequence of labels, conditioned or given these entire sequence of words. There are many flavors of this idea. To do this, we need to actually, realize this idea. We need data. In this case, the data set, or at least one of the data sets that exists, it's called the Penn Tree Bank. It's the oldest one of this kind, from '93, where a bunch of linguists wrote down the parts of speech for every word in every sentence of Wall Street Journal from 1989. And so you can imagine it's a painstaking effort, But once you have that, we can start building models. So this is another sort of a powerful idea that keeps pervading across natural language processing, where we have a bunch of experts who are trained in linguistics or say some other related fields who annotate text, and then you just give it as input to machine learning systems, and they learn these models that can mimic the experts. Another task is something called information extraction. You're given some text, and you have to, as the name suggests, extract information from it. What kind of information? Imagine that you want to build a database of all the entities and events that are mentioned in the text. For example, I want to build a database of all the names that show up and all their types. So Martin in this sentence is a person, Bananaville is a location, and Bananas Incorporated is an organization. So this is again another task where there are standard data sets where we can build statistical models, but here we need to introduce some domain knowledge. For example, we can say usually anything that ends in an INC is an organization. Most of the time, people are not named INC dot. So I can safely say this is an organization without actually knowing too much about these things. So we can introduce knowledge about the world and how the language reflects the world. Let me show you another example. Another task is sentiment analysis. The task here involves predicting whether some text has positive polarity or not. So you can have a sentence, the movie was so awesome that I want to watch it again. It's a positive review. The movie was terrible is a negative review. A slightly more nuanced negative review is the movie feels like they finished filming before they completed the script. Clearly, it's a negative. I mean, I don't want anyone to say anything like that about a movie that I make. If I make a movie, it'll probably be like that. But it's clearly a negative review without using any negative words. So it's not just looking up a dictionary and saying, oh, bad, terrible is a negative word, awesome is a positive word. And we can say more complicated things. The movie was long and convoluted. That's a bad thing. But maybe I can end the sentence with, but I liked it anyway. So that makes it a positive review. So sentiment analysis can be a rather nuanced task, and it can be framed as a classification problem where you have the input is the text of the review, and the output is thumbs up or thumbs down, yes or no, true or false. The sentiment analysis is a rather useful task, simply because we can use it, for instance, we can use it for deciding whether the sentiment about a stock is positive or not, and use that to base my investment decisions. I can be monitoring Twitter for what people are thinking about a certain stock. And if the sentiment is very negative, I can use that as an indicator that, oh, you know what, the stock price is going to tank. And it ends up becoming a one piece in a larger automatic investment system. So once again, it turns out this is also powered by probabilistic models, where we have data sets annotated with sentiment, and we can train models that take the text as input and produce a label as an output. I'm going to show you one more task, at least one more task, where things are not this easy. Not saying that this is easy, but things are going to get more complicated. Imagine I have to write a program that takes this italicized sentence as input. The input is a Python function that takes a name, prints the string hello, followed by the name, and then exits. And my program has to read that text and produce this as the output. It produces the hello world Python program. So the output is now a program. Or I can ask, find the largest state in the United States. And I can convert it into this formal query that that tells you, that if you execute against some sort of a database, it will give you the right answer. These kinds of problems are rather difficult. Even creating labeled data for these kinds of problems is difficult. But this is really what we would like our systems to do. we would like our systems to, when I say our systems, I mean your virtual assistants and all these things. When you tell a virtual assistant that's not going to be named right now because it will wake up, if you tell it to play some music after checking my mail, it has to execute a sequence of steps. In other words, it has to convert it into a program. Or I can say, tell me the largest state in the US and also text the name to my friend. So it has to convert that into a sequence of steps. And once again, essentially what these things are explicitly or implicitly doing is some sort of semantic parsing. Now, what we have seen so far is that language is rather can be rather ambiguous, can be complex, can be diverse, and these kinds of complexities can manifest themselves in many different ways. It can be lexical, it can be structural, it can be semantic. And the amazing thing is that the same family of methods, or the same high-level family of methods, excel across all of these, namely data-driven methods. I was telling you about the IBM team that used that kind of pioneered a lot of the machine translation stuff, like that is a grandfather of or grandparent of Google Translate, if you will. There is an anecdote from the person who ran the team, Fred Jelnik, apparently said, every time I fired a linguist, the accuracy got better. So the idea was statistics or statistical methods are so much more informative than we give it credit. But really understanding text it requires the interface across a lot of ideas. We need to have some sort of a statistical component. That's pretty much well understood today. We need to be able to build the right text representation. This is an idea from good old-fashioned AI. Actually, what we need to do in order to understand language is we need to understand both the linguistic aspects of it and the context in which the language is going to get used. So now, actually, can you just hold on for a minute? I'm going to pause. I need to take a short break. If you don't mind, I'll be.
Yeah, we usually do 5-minute breaks. And let's just take our 5-minute break now and reconvene at 1:11. Okay, Vivek, if you're ready, we can
Yeah.
resume.
Yes. Yeah, sorry about that. I had to abruptly leave because there was a knock on the door that didn't go away. Anyway, so what I was talking about is the idea that in order to understand language, we need the combination of multiple different ideas. We need to understand statistics. We need to understand the language. We need to understand the application. But things are still not, it's not like everything's a solved problem. For the rest of this lecture, I'm going to talk about the research frontier. And something that is of great interest to me, how do we reason about the world using language? So let me give you an example of a task called natural language inference, where you're given a sentence, a premise. Before it moved to Chicago, aerospace manufacturer Boeing was the largest company in Seattle. And the hypothesis is, given the premise, can you tell that Boeing is a Chicago-based aerospace manufacturer? And the answer is, I think it is, yes, it is, because it moved to Chicago. And there are these standard textual entailment or natural language inference systems, which will tell you that it's quite likely that the premise entails the hypothesis. And I'll show you a working version of this demo afterwards. And we can, and I would also like suggestions from the audience on things that we can put into the demo. But before that, another sort of an interesting place where natural language processing can be used, or at least something of interest to me, is thinking about how we can use NLP systems for improving mental health. There's a long history of therapist bots in natural language processing, including ELIZA. If any of you use Emacs, you actually have a version of ELIZA running in your computer, and I'll show you a version of it and we can chat with it for a bit. But let's think about what a trip to the therapist might entail, or a trip to any doctor. There's diagnosis, there's treatment, and then there's evaluation to see if the treatment worked. Well, with a therapist, the diagnosis is two people talking. The treatment is also two people talking. That's what therapy is. And the evaluation after treatment is also two people talking. There's a lot of talking, which means that there's a lot of room for automated text processing systems to maybe help. Mental therapy is essentially a dialogue between people. So we can ask questions like, is some treatment better than the other? Is some counselor better than the other? Is the patient really getting better? And we can even use NLP as a tool, for example, to understand how psychotherapy even works. It's a collection of NLP problems where we want to, make sense of hours of rather emotional dialogue. We can, for example, build a therapy bot like ELIZA. We can build a client bot. For some reason in counseling, the patient is called a client. So we'll call it a client bot that can be used to train therapists without actually inflicting them on real people. Or we can have a assistant that just watches the therapy session and asks, keeps track, oh, is the therapist doing the right thing? Well, NLP can actually transform mental health among other fields, but of course, there's a long way to go. There are many different challenges in these kinds of things. There's a question of, whether, what is a good representation of language? And we need to understand whether how to get around this need for data. Annotated data is so precious and so hard to get that we need to understand, can we build modeling systems, natural language processing systems that don't need so much language data? There's also the question of efficiency. Today's NLP systems are ridiculously compute hungry. There was a paper in 2018 that talked about how training a certain model called BERT, or or a version of it, used up so much energy from the cloud compute system where it was trained. You could actually fly to Europe if you were willing to burn that much carbon. So it was as much carbon as much carbon consumption as a flight across the Atlantic Ocean to train one model. So, what if I want to scale these systems to every doctor and every patient and every clinic in the world? And For me, the more interesting question is about reasoning. How can we build systems that reason about the world? Let's talk about very briefly about programs that reason about the world. Here's a photograph of a sculpture of Aristotle, who talked a lot about logic and reasoning in his time. The question to you, everyone, is did he have a laptop? Anyone? So, I mean, most of us will say no, right? Isn't that amazing? Where did you read that? Did you read a book about Aristotle not having laptops? Did you know it from, did you see this in school? Was he too poor to get a laptop? What was going on? To answer such questions, we need to think about how the world works. We need to think about more than just parsing the text, more than just doing sentiment. We need to have a model of how the world exists. We need to understand that people cannot own things that have not yet been invented, for example, or people who have died cannot own things. And the challenge is, can programs do that? What we want are programs that can read, understand, and reason about text. Well, actually reason about the world. And so far, it's a fast-growing field. Some things that we know are the representation of text matters. In this sense, good old-fashioned AI was right. Statistical machine learning is a tool that's here to stay, and data-driven compute is the right paradigm to think about this. Knowledge helps. Knowledge about the world, knowledge about the application, knowledge about linguistics. And if you have good data, it's going to make a big difference. So natural language can be fun, but it's weird. I mean, it's really weird. I have a big growing collection of weird linguistic quirks. This is one of those strange hobbies that one develops if one spends enough time doing the kind of work that I do. But that's the fun part of it. I think the vision of computers dealing with human language is so pervasive that it has been around since the birth of computer science. What we want are programs that can accumulate knowledge by reading, rather than us programming it in. That way, I can unleash the program in all the libraries of the world and then help me solve my physics homework. Or I want programs that can answer questions. Like, would it be easier for me to fly from Phoenix to Salt Lake City or to drive on Sunday? It depends on so many things. It depends on the traffic. It depends on the weather. It depends on the flight costs. It depends on my car, whether it can actually make it to Phoenix, and it depends on whether I'm a good driver. So there are so many complicated sort of things that it needs to do in order to reason. Can it do things based on my instructions? In science fiction, you see people talking to robots, but for that it needs to understand what the person's speaking. So if I tell my PowerPoint, change the first 15 slides in my presentation to use the new slide, my PowerPoint is not going to do anything. I have to manually do that work. So can we actually convert this command into a program? And there is, English is not the only language out there. Can we, if statistical NLP depends on data sets that require dozens of linguists who have collectively dozens of years of experience to annotate the lot of text, how on earth are we going to scale this or replicate this for other languages like Swahili or Balochi? And at the heart of it, that this is where the fun part of it, the heart of it is, what does language mean, and what does understanding mean? And it forces us to think about the something that's uniquely human. So I'm going to pause, ask me questions, and I don't know how long we have. And in the rest of the time, I would like to spend showing you demos of NLP systems that exist. I want to show you at least two kinds of demos, one of a very old system, ELIZA, and one of a rather new system for natural language inference and maybe reading comprehension. So I don't know how long we have, so we can
have
spend
24 minutes. So
excellent. So then we can do a lot of demos. And please ask me questions, and ask me questions now or afterwards also. You feel too shy. While you're thinking of,
there was one question earlier that I couldn't squeeze in at the right time. Would you make a database for common idioms?
Oh, yeah. So we could make a database for common idioms, except what about uncommon idioms? What about idioms that are made up on the fly? And usually that does happen. We do end up having databases of idioms that we can just use and hope to rely on statistics for uncommon idioms. So that's a very popular strategy where if you can use a rule to solve the problem, then use the rule-based system. If not, build a statistical thing. And really, this interplay is something that is interesting. I'm going to stop sharing because I want to share a different window, but please do think of questions, ask questions, and
I've got a quick question. I know that English is one of the hardest languages to learn. So I was curious if there are other languages that lend themselves more easily to NLP versus English.
Oh, actually, I would argue that all languages are extremely hard to learn. In fact, there's some very cool work from a bunch of people from UPenn and Edinburgh, where they talk about what is the complexity of the syntax of language. And it turns out that all human languages are roughly identical in that sense. Essentially what all languages need is recursion. We need to be able to construct complicated things by composing parts. And beyond that, there are, it's mostly minor nuances. But frankly, all languages are roughly equally hard to learn. One might even argue that English is actually kind of easier to learn because it's more forgiving in terms of the exact right inflections that you need to add to the end of words. Other languages have more sort of strict rules on how you should end a word in a certain context. Any of you who learned Latin, and I'm hoping it's nobody, would appreciate what I had to say, or any of you who watched Monty Python and the Holy or Life of Brian would recognize the joke from that movie there. But once again, I have to resist putting Monty Python jokes in slides, so I won't. There's a question.
You don't. It's perfectly acceptable.
No, it's fine. There is a question: can a computer, quote, understand something? That's a good question. What does understanding mean? Is it enough to just simulate understanding? If you have a program that gives you the right answer to every question you ask, no matter how complicated it is, does that program understand language? Does the program understand something? This is also the basis, for example, of the Turing test, where the goal of deciding whether something is human or program, the task is to decide whether something is a human or a program. And if a person cannot tell, then the program has passed the test. Turns out it's kind of easy to pass the Turing test because we are very forgiving. There are other interesting tests, like tests of reasoning, like say, can the police were afraid that, anyway, there are these tests of reading comprehension. I have to kind of, it involves cleverly constructed sentences that people will have no trouble understanding, but a computer would have to understand, prove that it understands something. The question of whether a computer understands something is a profound question that is it's going to take far longer and many years to resolve. And maybe we shouldn't open that can of worms right now. All I want to say is that it is a good question, and keep thinking about it, because that's what we need to do. So the first of my 2 demos is ELIZA. I hope you can see my terminal or my Emacs.
Yep.
Yes.
Okay. Any of you who use Emacs can just type meta x doctor and get to this reproduction of ELIZA. So I can say things like, and ELIZA will respond, why do you say you're hungry? And this, keep in mind, oh, by the way, I don't know if the font size is too small.
That's good.
Okay, keep in mind, this program was entirely hand coded. There is no statistics here, no data science. And I can basically maintain an infinite conversation with this, and it will tell me really profound things. That I didn't have lunch today. I don't have any plans today because of my life. And this program was written in 1966. So I think it's pretty cool. This is before we had computers in a recognizable form, and it's the fact that it still works is quite impressive. But I don't want to spend too much time with ELIZA, and I want to go
Just one
another
more
set of.
question, if I can interrupt you. What about languages where individual characters have meaning, like character embeddings make NLP for Chinese easier?
Oh, that is such a cool thing. So it turns out that the word embeddings, when I describe them, are just the first or the coarsest of these ideas. Most of the time, we don't have word embeddings that are just a mapping from a word to a vector. Usually, these word embeddings are constructed from the underlying components. So for instance, if I have the word diplomat and the word diplomat, the word S at the end is just a plural indicator. You can attach it to any word and you get a plural, any noun and you get a plural. So the meaning of the word diplomat is, in some sense, the combination of the word diplomat and this plural marker. And this sort of character level combination is how a lot of word embeddings work today. Character embeddings may make NLP for Chinese easier, or it might make NLP for Chinese harder. I'll tell you why it might make it easier, because the single symbol carries so much more meaning than a single character in English or any language written in the Latin script. However, if you know Chinese, think of the number of symbols there are. People spend a lifetime learning the symbols. So it's not necessarily that simple. Another question: does poor grammar and misspelling add too much difficulty? Yes, both to people and to computers. So it turns out that spelling is such a modern phenomenon. The idea of spelling being normalized is only from maybe the 16th or 17th century, from the first dictionary. So if we think about how spelling makes a difference, if I have a word and I'm just making minor edits to it, I want the embedding for that word and the misspelled version to be similar. And if you're constructing the word embedding from the pieces, it allows for that rather than just looking it up. Now, poor grammar is a different beast. Grammar is a rather fluid concept. We are taught that every sentence should have a subject and an object and such things. But then imagine that there is someone enters a room and screams fire. They have not used a subject. They have not said that thing in proper grammatical English, saying, "Excuse me, sir, there's a fire in the building." No, they just scream fire and you run. So you know exactly what they mean. So communication does not, grammar is needed, is nice to have for communication, but often when we process text or when we process language, we mentally can actually elide over poor grammar. So if we build models of language from statistics, from statistics, using statistics from data that is written by people, the data will have poor grammar, and automatically the model also kind of learns to elide over poor grammar. So we can play some, we can try this out on a few demos, and there's some chance that everything that I said will fail because these are statistical systems. But let's see. So I'm going to walk you through a few example tasks. The first one is this task of sentiment analysis, where we have to decide whether an input text is positive or negative. So let's see, I'm going to use this model called Roberta. It's just a state-of-the-art system today. And let's first start off with some examples that are canned. A very well-made, funny, and entertaining picture, and the model will say, the model is very confident that the sentence has a positive sentiment. I can replace this with a very well-made, funny, and entertaining picture, but a total disaster. And at this point, it still says it's a positive sentiment, so the model's already failed. Let's use, here's the sentence, so unremittingly awful that labeling it a dog constitutes cruelty to the canine. I don't know what this is about, but I can say for sure that this person does not have a positive emotion, and this model gets it right. By the way, you do feel free to add, if you want me to try out something or make some changes, feel free to mention that in the chat. There's a question. You've seen AI trained to paint pictures. Would there be a similar case with this? Can a bot write a book based on a set of parameters? Okay, you ask for it and I deliver. Let's see if a bot can write a book. This is a task called language modeling. The model that is behind this demo is called GPT-2. Today, the best of these is called GPT-3. Some of you may have seen, if you search for GPT-3 in the news, you might actually find rather interesting, sometimes apocalyptic statements about it. But what it does is it predicts the next word given the context. So I can say it was a dark and stormy, and ask the model what comes next, and it'll say night. The wind was awful. By the way, there's a probability here. The wind was awful, and I saw quite a few people. There is a story that's forming here who looked like I had seen. It'll stop. Oh, look, night. I had seen a lot of things. There was something about Chernobyl after that. I don't know what the sentence means, but you're getting something. So now a question that I want you to think about is, does this system actually understand what it's talking about, or is it just gluing words together? Does it have, if you want to write stories, write a book based on a set of parameters, it's also worth thinking about, is there a plot? A book is more than just one word next to each other. There's a plot, there's a structure, there is character. And this model does not have any of that. The GPT-2 or GPT-3 models don't have any of that. There's another question with AI in general, though it applies to NLP. How do you deal with the ethical complications? This is brilliant. In fact, I was literally just going to bring that up. These models, unfortunately, they are trained on a lot of text, and they end up embodying a lot of stereotypes and biases that are in the text that they are trained on. Unfortunately, for example, a lot of word embeddings you can easily coax a word embedding into confessing that it believes that doctors are men and nurses are women. Even though this is there's nothing that makes this true in the world, we can see most word embeddings somehow embody this bias. Similarly, There are there are ethnic biases, there are racial harms that can be made by these things. And you can quickly imagine what would happen if this kind of a model is let loose in deciding whether someone should, a CV should be interviewed or not. There is a famous example of Microsoft's bot on Twitter that was trained by Twitter to become racist. So this is a big area of study. How do we build AI systems that embody that encode some sort of a fairness in them, fairness and accountability and transparency of what they do? This is a super hard question. It involves more than just computer science. This is, in my mind, one of those areas where a purely technology-driven solution is not going to work. We need to involve people. We need to involve people from other walks of life. And we need to involve, a diverse collection of people. This is one of the places where, if we don't do that, it will lead to bad outcomes. So I'm not going to say that we have an answer. All I know is that we have problems. There was a question that I missed, right? How sophisticated is NLP when it comes to topic modeling? So topic modeling is a good first cut. I don't know if you've covered topic modeling in the class, but topic modeling is this task of deciding, essentially clustering the words and deciding, looking at the clusters and seeing whether it belongs to this topic or that topic. And if you cluster all the words in a newspaper, you might get a cluster for, say, politics, one cluster for entertainment, and then you could essentially you can get a zeitgeist of what is the newspaper talking about. Topic models are a good first pass for sort of exploratory analysis, but often if you want to ask pointed questions, it's better to have specific task definitions. For example, you can look at a task like textual entailment here. Let me pull up an example. This was the task that I described. So if you help the needy, God will reward you. And this is the premise, and the hypothesis is giving money to the poor has good consequences. And you run the model, and it says, with high probability, with 76% probability, the first sentence entails the second. And we can try more fun things. So let's say that an interplanetary spacecraft is in orbit around a gas giant's icy moon. That's the premise. From this, can we tell that the spacecraft can travel between planets? Well, of course we can, because that's the definition of interplanetary. Let's see if it says anything. And here's where the model fails. It's very likely that there is no correlation between the premise and the hypothesis. So this is one of those places where the system fails. One of a hobby that I have involves pulling up these kinds of demos and making them fail in interesting ways. Turns out you can make them fail very easily. But it also tells us the limitations of existing systems. Let's do one more example. So I can look at reading comprehension, say. So there was let's see. I don't want any arithmetic and stuff because it will totally fail. Yeah, let's take this one. Who stars in the Matrix? So here's the Wikipedia page of the movie The Matrix. And the question is, who stars in The Matrix? And the answer is exactly this list here. And the goal of the model is to find it. And it actually does. Of course, we can make it fail quite easily. This model is again built on top of word embeddings. All of these, this Elmo here is a word embedding, Roberta is a word embedding. All of these are different word embedding systems. So effectively what we have here are really complicated neural network models that run on these, that are trained on hundreds of thousands of examples. Together, these represent sometimes billions of parameters to decide, to answer the question by deciding where is the starting point of the answer and where is the ending point, and everything in between is the answer. Hey, are we out of time? I can keep playing with demos, but I don't want to keep you longer. So when does this end?
It's at 1:45, so we have 5 minutes, but we can maybe take a question if anybody has one.
Yeah.
Can you talk about how Watson was able to decipher complex Jeopardy questions?
Yes. So Watson's kind of cool. Watson is an incredible engineering effort. So those of you who've not seen Watson, it was a system built in 2013, I think 2013 or 12, which beat the world champion at Jeopardy. At that time, so Watson is really a massive ensemble, a collection of many, many different pieces. There's like a little expert, for example, who was, I'm anthropomorphizing these systems, but there was a little expert inside Watson whose only job was to know about, say, how calendar dates interact with each other, how days on the calendar interact with each other, is a day before or after. So you have many different pieces of knowledge and many different experts on very specific things. And then on top of that, there was a classifier. The job of the classifier was to take the question and decide which expert should I call in order to construct the question. In Jeopardy, you're given an answer and you have to create the question. So the answer is, you're given an answer and the context, the type or something like that. And you have to create the question. And given the answer, first you decide which expert, and then you have to essentially search over a database of entities and events and such things. And you have to, if the question is easier to construct. For example, if the question is, say, Keanu Reeves, so if the answer is Keanu Reeves, the question could be, who was the who starred in The Matrix? So I can construct it. It was really a complex set of multiple agents, and there was an ensembling thing on top which connected, which decided which expert to call, and another ensembling agent that talks about how to glue them together. In my mind, Jeopardy is truly amazing feat of engineering. A lot of the work that went into it was already there. I mean, it was from the research from the decade before that, but putting them all together required an organization like IBM because it required a lot of engineering chops. Yes, actually, Ken Jennings does have a good TED talk where he talks about this.
Okay, unless we have a last question, let's all thank Vivek. Thanks very much for a very informative and entertaining lecture.
Thanks.
Yes,
Thanks
thank
that
you.
you took the time.
Thank you.
And if you have questions later, you can send me an email. I